Good evening, my name is Lee Theodore. I'm the project coordinator for Future Climate Leaders. Today we are gathered together at the St. Lawrence River Institute. Today we're having a fantastic conversation with Dr. Chris Byrne, who's come to us from Carleton University. This is a gentleman who specializes in permafrost, but better than that, he's here to talk to us about climate change. For those of you that are in the audience, having a good time at home, enjoying this conversation, you're welcome to interrupt at any point in time. This conversation will be well more interactive than the previous ones before. So we invite you at any point in time. I'll be moderating the Facebook comments. And if you have a question, I have a question, Dr. Byrne will interact with you through me. For those of you that are here, the information instructions are the same as well. If at any point in time you have a question, you'd like to engage, Dr. Chris Byrne is the kind of guy that likes to engage. Feel free to engage with them because that's what gets the conversation going and that's where the magic of this happens. So without further ado, I very much appreciate your time and attention. Please enjoy this talk. And we look forward to what follows afterwards. Dr. Chris Byrne, please have a conversation.
Well, thank you very much, Lee. I'll just bring our little chair across here and we'll sit down, I hope. There we go. So I'd like to thank you very much for welcoming me here to the River Institute in Cornwall. I've had a wonderful day so far. I spent 2.5 hours with some of the first and second year environmental technology students. And even though they were only meant to be there for 2 hours, they were still there at 2.5 hours. Nobody left until the end, and there was good food to keep them there, but there was no punishments if they left early. So that was really nice, and it was very, very enjoyable to talk to all of them. They were very engaged. I'm going to talk to you today. My work is mostly in northern Canada, in the Western Arctic, in the Yukon and near the Western Arctic coast. So what I'm going to talk to you about comes from there. But really, some of the things that I'll speak to you about, even though they are quite a long way away from here, they do actually affect what happens here. The one thing I would say, because I'm a university professor, I always like to give people reading to do. And there is this little book. It's in the series, which is called A Very Short Introduction, by Oxford University Press. They're about 150 pages long. This is the 4th edition of the Very Short Introduction to Climate Change by Mark Maslin. And it's a very nice, simple, 9-chapter introduction to all different dimensions of climate change. Some political, some scientific, some in terms of community action and so forth. So if there's one book that anybody wants to read about climate change, or one book anyone feels they should read at least one book, then I would suggest you read this. It's quite short, it's quite small, it fits nicely in your pocket, and it's got a nice attractive cover. So that's the one that I think is good. So should we be concerned about climate change in Canada's north? That's the topic for today. And what I'm going to do is to go through I'm hoping to advance this slide. Oh, there we are. So we're going to start with thinking about the north. So, have any of you been to what we might call the north? What's the furthest north? Zach, where did you say you went to?
Whitehorse.
Whitehorse. Now that to me is bona fide north, because it's north of 60. And did you go any further north than Whitehorse?
Just a little further, maybe 3 hours into the mountains.
Did you go, was it near Carmax, or did you go to Kluane?
West. Neither of those is just right north of Whitehorse, up into the mountains, pretty much.
Okay, by helicopter, or did you walk?
Hike,
yeah, so nice, huh? Nice area,
beautiful. Very
nice. So some of the pictures that we'll have in a minute are actually from that, not from that area, but from near that area. Anybody, yes?
So I'm not sure how far north would north be. How far south into BC would be considered north? Would there be any considered north?
Well, the University of Northern British Columbia is in Prince George.
And Dawson.
And Dawson Creek is a little bit further north than Prince George.
Okay.
So Dawson Creek, people would say, is, well, it must be north because it's north of the University of Northern BC, right? So I don't know, but it's kind of a little bit of a flexible definition where the north is, but the one that is used most commonly by the federal government is that the north is where there's permafrost. And permafrost is ground that remains below zero for 2 or more years. So it's sort of an area north of permanent freezing. And that's what, when they give grants to students to go and study in the north, that's the definition they use. If you're working south of that bottom of that yellow line, which is the southern limit of permafrost on this map, they say, no, we're not going to give you any extra cash. But if you're going north of that line, then you're eligible for a little bit of extra support to try and get there. Now, on this map, which is in a number of colors, because it simply represents how much of the ground has got permafrost underneath it. And in this purple area, basically everywhere has permafrost underneath it. And in the pink at the bottom, it's only seasonal, so it's only frozen like it is around here. So Cornwall, which is down here, is in the pink zone, right? Because we get frost in the ground in the winter down here. And then in the yellow zone is like between nothing and 10% of the ground might have permafrost. And as you go further north, of course, there's more of it. Most of the places that I work are in the central Yukon, a place called Maheu, small community of 300. So it's not huge. And then in the Western Arctic, out on the coast, there is this red zone of permafrost, which is permafrost that's under the ocean. It used to be under the land when the ocean level sea level was a lot lower during the last ice age. But climate change, which is moving from an ice age into an interglacial, has flooded that area. So it's now entirely submerged. And so there's that area, but most of the area is terrestrial. So I'd like to ask you, in the context of climate change, you probably know that in the 90s especially, and in the early 2000s, climate change was fairly controversial. There were people who were deniers of climate change, and then there were people who thought climate change was an inconvenient problem, and then there were other people who believed that climate change was real and was going to happen. So one of the questions that climate change raised in my mind in the 80s and in the 90s and the 2000s was constantly to ask myself, why do I believe that climate change is actually happening? And I'm using that word carefully. Why do I believe in climate change rather than knowing about climate change? Mackenzie, why do you think I was posed with that problem?
I assume because you hear different perspectives from people around, mostly probably politicians that would deny it for their own, not necessarily for their own benefit, for the people that give them money. So
there's people who were saying that there's no such thing as climate change, or they're saying that climate change is not real, or they're saying that climate change is not happening. But at the same time, there's this big international movement that is leading us towards the Kyoto Protocol, which is the late 90s. So there's something going on where there's people saying we've got to get lots of people together to work on this problem. And then there's something else going on which is saying this is a load of rubbish. And there was a tension in the 80s. At one point I had a conversation with the Federal Minister of the Environment at the time, whose name was David Anderson. And he told me, he said, Chris, you will not believe the amount of money that was spent lobbying me to make sure Canada did not sign the Kyoto Protocol. Lots and lots of money was spent so that we didn't reduce our emissions or begin to reduce our emissions. So it comes back, I think, fundamentally to one of those kind of almost metaphysical questions, which is, what is the difference between knowledge and belief? Because I felt I knew that climate change was happening, but there was lots of people outside who wouldn't share my view. Jacqueline, why do you think they didn't share my view?
Because they thought it was a bunch of rubbish.
But why did they think that?
Because they kept being told it was rubbish.
So part of the way we get our knowledge is from what we're told, from
Yes.
other people. But in science, we don't always just believe what we're told. What else do we use to think, what to make us understand or believe something?
Facts, experiments, first-hand
Those things.
travels.
Those would be things we call evidence. Would be, so observations that we make. And one of the problems in the 1980s and the 1990s was that climate change, due to what we're experiencing now, hadn't been going on for very long. So people could make the argument, well, it's just a small little cycle. There's always ups and downs, and now we're going through an up period at the moment, and don't worry, in 10 years' time, it's going to come down the other side of the hill. Right? The problem was it didn't. So that's one of the things. And then the other thing is that we do sometimes get what we know from somebody who's established a theory, a series of ideas that we put together that we've found to be consistent with the way we understand the world is. And the difficulty there with theory is that you don't accept theory until it's supported by evidence. And even if you don't accept theory, then it's not a fact. If it's got to be more in the realm of belief. And one of the things that we're a bit bad on in the public sphere is accepting belief. What I use as a very helpful definition of science is that science is the construction of well-motivated belief. That is, of things that we have really good reasons for holding to be true. So, for example, only one person, I've only lost one person in my family due to COVID. The rest of our family all went and had 2 shots in the arm. We didn't know that was going to stop us from getting COVID. We actually have had members of my family who've had 2 shots and got COVID. So it didn't stop them getting COVID, but we believed that it would really help. And that's actually what happened. My sister and her husband got COVID, but they'd had 1 shot, so they had 2 weeks, which was not very pleasant. But they're still with us, thank goodness. And they'll be with us for many years. Right? But that was because of a matter of belief. They believed that if they got the shot, it would be something that would work out well for them. And so I think there's a difference between knowledge and belief, but so much of what we do is associated with our beliefs. But we have good reasons for believing that. And that's really kind of what science is all about, is in the business of creating belief, but having a very good reason to hold that belief. So now let's look at the evidence for climate change in Canada. And this is a map, and it shows how much the annual air temperature at places across the whole of the country has changed since 1946. It's a map that was published by Environment Canada in 2015. And you'll notice on this map that there are a couple of really significant differences. John, what are they?
Well, I
can you see it?
Barely see the one, but yes.
Yeah, well, I'll duck down and then you can see lots.
The significant amount of warming in the northwest.
In the northwest, right. So that's where that red is today. It's the hot spot. So that's one thing. And the western side received a lot more warming. And the other thing, you also mentioned it actually when you said it's not just the west, but it's also
the north.
The north, okay. So the north has got more warming than we have had in the south. So that's kind of the national picture. And this is basically data that's collected on the basis of weather stations all the way across the country. So this isn't just like 1 or 2 spots. But if we look at the record from both Inuvik and from Ottawa, so Inuvik is in the top northwest side. Ottawa is, we all know where that is, as far away from here as we'd like it to be. How far away is it?
100 and some odd clicks.
100 kilometers? Well,
That's a little more than that.
Little more than that. Make it as far as you want. That's right. Anyway, so since 1971, the mean annual temperature in the Mackenzie Delta has gone up by about 3.5 degrees. So from about minus 9.5, it's now sitting at about -6. That's sort of the maximum for Canada in terms of rate of change. For Ottawa, it's from about -6 or so to about +6 to about +7. So it's gone up by about a degree down here in the south. And these lines are averages of 10 years. So it's not like 1 year's climate, which would be really jumping all over the place, but I've taken a 10-year average and rolled it up and moved it along. So if I'd just put singular values for individual years in the Western Arctic, so that would be up. Is this arrow showing on here? No, it isn't.
Oh, we were going away.
You don't. Can you give me a pointer? Oh yeah, well, up on the top right-hand corner.
Got it.
Okay, so that's the Mackenzie Delta, and it's the left-hand axis. So the left-hand axis is -6. But in the last couple of years, the annual value has been much closer to -5. So it's a substantial increase when you think that 3 degrees difference in temperature is about sort of between Cornwall and down south towards Washington, D.C. Right, so it's that sort of big difference in climate in 50 years. So that's within our lifetimes, or most of our lifetimes. And that's not something that has been made up. Right? This is something that's actually measured. So in a sense, it's real. In Ottawa, not so much. But that's the context of climate change across the country. And then if we look at what happens specifically in the Mackenzie Delta area, and the left-hand slide here, the left-hand picture, is the value from Inuvik, which is the same, the line is the same line as I gave you before, but the dots are the individual years. And you'll see those very high dots right at the end of this series, up in the 1920s, 2019 and 2020. They're way up top, near to between -5 and -4. So even warmer than we anticipated. Now, what I'd like you to notice about this on the left-hand side is its temperature. And you'll notice that not only is there variation up and down, but there's also a gradual increase. So the pattern of the increase is something that we can follow, which is an important point. On the right-hand side, we look at the rainfall. Now, you look at the minimum rainfall is about 40. What I've done is I've ordered them all from highest rain to least. And we've got 40 centimeters of rain as the least they've had in a year, and about 240 is the most they had in a year. So there's a huge difference. And it's very, 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 very variable, which means that it's actually difficult to say that this is what's happening in what we call a statistically significant way. So the things that we do in statistics to say that this change is not random is a difficult thing to do. But we should point out that if we take the top 20 years, the highest 20 years, 11 of them have been in the last 20 years. And if you had 60 years and you chopped it into 3 parts, then you would have 6 or 7 of each group, the highest, the middle, and the least, in each of those 20 sections. But we've got 11 of the last 20 years are in the biggest rainfalls that have ever been, rainfall that has ever been measured in that area in 60 years. So what that suggests to us is that the rainfall itself is changing. There's too much variation to be able to say it in the same way as you can say it with the climate, with the temperature, but all the evidence is there that is suggesting that this is what is happening. And this is the sort of problem that we run into, is that it's not statistically what's happening, but we can see it happening in front of our eyes. So then the question is it a fact or is it a belief? And that's actually quite a significant problem, because if we're going to make decisions, we have to make the decisions. Usually people say we want facts before we make decisions. But this is a sort of evidence, and in itself it's a fact, but it's not saying that it's as secure statistically as the temperature is. So this is part of where I think Mackenzie's quite right about saying how people, didn't really know how they could support the nature of that climate change before enough data had been accumulated where it became absolutely clear that was going to happen. So when we look at the Arctic, we have extra warmth in the Arctic, we have extra precipitation in the Arctic, and together this is what we call Arctic amplification. That the climate change that we know is happening in the Arctic is greater than what we observe down south. So the first question is it well motivated? Rachel?
Yes.
Rachel, yes it is. I agree. Right? So it's well motivated in the sense that there's data that suggests that the climate change we observe in the north is greater than what we observe in the south. So it's a belief, because we don't have perfect information. Like there's not many stations in the north, but there's enough for us to say, yes, this is actually what happens. So then the question is why? Why is the Arctic, why is northern Canada one of the hotspots for climate on the Earth? Katie, I haven't asked you yet.
Sorry, can you repeat the question,
Yes,
please?
why do you think our Arctic is one of the hotspots for climate change on the Earth?
Because in Canada we have a lot of hotspots for it too.
Well, we've got a lot of hotspots in the north. We don't have so many in the south. But why is there so many more in the north?
Because I'm not sure.
Okay, so what do we think of, when you think of the north, what comes into your mind?
Well, it's colder.
It's colder. And so when a change happens, if there's a place that's already warm and it gets a little bit warmer, do people think there's been a big change?
Mm.
If there's a place that's cold and it gets a bit warmer, what do they think? They think climate change. They think it's getting warmer. And part of what's happening with climate change is that the tropics, like the middle of the Earth, is where all the energy comes in, because that's where the sun is beating straight down every day. So it comes down, it warms up the air in the tropics the most, because that's where all this energy is coming in. And then the energy goes from a place that's warm to a place that's cold. And it ends up in the place that's cold. So it moves from the warm tropics up to the Arctic, and it moves in storms, and it moves in warm air that's traveling. But it doesn't stop as it's going towards the north. It stops when it gets to the north. So the north receives all that energy transferred in the weather systems that are moving around the Earth. So that's part of the reason for what we call Arctic amplification. In fact, the extra warming at the tropics is taken away from the tropics and is put into the Arctic. So that's one reason. Thank you, Katie. Well, can you think of another reason that's sort of related to it?
Sorry, I can't really.
Okay, Rachel. You're smiling, so
got
you.
me on that one.
you
I'm
got-
listening. I'm
Yeah.
listening.
Mackenzie?
I think it's something to do with the ice caps.
Yes.
As they melt, there's less albedo, which is the reflectance of the light. So it results in more heating. It's like a positive feedback.
That's right. So in the summertime, especially when there's lots of sunshine, like the number of daylight hours is very high, there's all this energy beaming in to the surface of the ground. And if it hits an ice cap or if it hits snow cover, it just gets reflected straight back out again. So, like when we go skiing, you always wear dark glasses. It's too bright because the energy that's coming from the sun is just being reflected straight back at you. Whereas if that ice melts, we've got bare ground. And then the energy that comes down, as Mackenzie says, it's just absorbed by the ground. So it's then available. So then that heats the air because it's heating the ground up. So that then makes the Arctic more warm, because previously there's not much. Down here in Cornwall, we don't have ice caps. So we have the same thing happening all the time here, whereas they've got a period where they had a lot of reflection and now it's less. So those two factors lead to what we call Arctic amplification. And it means the Arctic gets much warmer than the South gets much warmer, which is what you saw on the line, on the lines on that graph. And so then this has implications for permafrost. And the permafrost, as I said, is the ground that remains below zero for more than 2 years. But for much permafrost, it's remained below zero for thousands of years. Now, I'm going to take you to a small place on the western Arctic coast. It's called Ilsavik. It's just on the edge of a little island called Richard's Island. It's about 70 miles, 100 kilometers north of Inuvik. And it's actually on the coast. And this is what Ilsavik looks like. It's absolutely beautiful for somebody who likes to go there. For other people, it may not be great because there's no power. It's really wonderful. There's no internet when we get there. It's great. No email for maybe 3 weeks. Oh, it's heaven. But it's a location which in 1978, one of Canada's chief permafrost scientists, the most well-known permafrost scientist, in some people would say in the world, but certainly in Canada, a man called Ross Mackay, he drained that lake. You can see the lake basin, and he dug a little trench, and the water started flowing out of the lake towards the ocean, and it cut a channel into the permafrost, and then it drained. The whole lake drained in 8 hours. It's about 600 meters long, it's about 300 meters across. And he did it because he wanted to study what happens when permafrost grows. Because underneath the lakes, we don't have much permafrost because they're a water body and they have ice on top and they've got water below. So year round, there's a temperature above zero in the water because the water doesn't freeze at that depth. So it stays without permafrost. And then you get rid of the lake and then you grow permafrost. And that's what he wanted to study. That was in 1978. And it's still going strong. It's Canada's longest Arctic field experiment. So I couldn't go there the last couple of years because of COVID, but some of my previous students very kindly went there and took the measurements that we take. So that's the location. Now, because it was a special experiment, and when you can see it on here, just there, he has a cabin. And that means we have a lovely place to sleep in the winter. And there's a stove and you can make it warm and you can cook in there. And there's no, you have to bring diesel to run the stove and we have propane to run the cooking, but we don't have to, there's no switches, there's no power or anything like that, but there's a place to stay. And that means that you can do work all year. Any time of the year you can go and work there and you'll be safe. Now on the hills around Ilsavik, not in the lake basin, but on the hills, we're able to drill holes and put temperature cables in the holes to see what's happening to the ground temperature. And the next slide, which is this one, shows 3 little panels, and each panel shows what's happening to the temperature in the ground at different depths. So the first one is panel A, and that's the temperature at 1 meter or 5 meters depth. So it's quite close to the surface. And you'll notice that when we put these cables in about 2008, the temperature is about -7. And then by 2018 or so, it had risen up to about between -5 and -4. So that's the ground responding to climate change. So it's warming up. Deeper in the ground, it's not warming nearly as quickly. And in panel B, you can see the change from about -6.5 to about -6 at 15 meters, and at 50 meters, going from about -7 to just above -7. But in panel C, what you're looking at is a temperature that goes all the way down in the ground. So it goes down about 50 meters into the ground. And when we made that hole, all we did was to use a water jet. We had a fire pump and we had a steel pipe, which is just like a piece of plumbing pipe, and the water comes shooting out But because it's going through permafrost, it just goes straight down in the ground. So we drilled it in about 2.5 hours. It was very quick. And there you have the temperature profile in the ground in 2007, and then another one about 11 years later. What you'll notice is that there's -8 on one side, -5 on the other. So that's the surface temperatures. And at 5 meters depth, you can see it's warmed right up. And then lower down, it keeps warming up all the way down, but the warming gets less and less as the depth increases. So we've got lots of energy going into the ground from climate change, and all of that energy, which is going down in the ground, is not just stopping at the surface, but it's going and warming 50 meters of ground up. And if we went further, we would go down to about 120 meters before we found that the ground wasn't changing temperature very much. So there's a huge amount of ground which is warming up. And if that ground is warming up, then the amount of energy we put into it to warm it up is going to take a lot of energy out again to cool it down again. So this isn't a change that we can reverse just like that. It's a change that actually is going to make a significant difference. It makes an impact because as the ground warms up, it loses its strength, especially because it's getting close to its melting point. Its thawing point is close to 0, and it's losing its strength. As it gets warmer, it loses its strength, and that means it has a more difficult time holding structures on top of it, like buildings or roads or airports. So the warming of the permafrost affects the infrastructure because of the change of the temperature. However, one of the things about this, and this is the temperature driving the climate change, is that the climate change is gradual. You notice that was 10 years of difference. So 10 years of difference is quite a long time. And being as a person like me, 10 years gives me lots of time to think about it. So it's not like, oh, what's happening? I don't know what's going on. I can say, oh, slowly, oh, there's all sorts of changes happening here. I think I'm beginning to see something that's real. And part of what happens with climate change is that we get gradual change. And if we have gradual change, then first of all, it's not going to be a great surprise as things happen because it's just a small change. And that's what some people will say is, oh, it's just a small change. Don't worry too much about it. And a small change is fine if it's 1 year, but if it's 50 years of small changes, that's a lot of change. The second thing about a gradual change, it gives us time to think about it. And then we can really understand what's happening. And if understanding is the key to adaptation. Because if we understand what's happening, then we might be able to manage it. If we don't understand it, we can't manage it. And then the third thing, of course, is that if it's happening gradually and it's constantly happening, then it's easier for us to tell somebody, well, in 10 years' time, this is what's going to be the case. So you better get ready. So in that sense, adaptation is easy with the gradual adjustments of climate. So now we're going to move to the rainfall and the precipitation. And the precipitation, as you know, happens in bursts. Like what's going on in British Columbia at the moment is not something that they expected 3 weeks ago. Maybe they didn't even expect it 2 weeks ago. About a week ago, they knew something was happening, that was coming. But now it's here. They don't have much time. And that's because precipitation comes in lumps, whereas temperature is a much more smooth kind of event and creature. So now we're going to take the right-hand side and look at what happens when we get very large rainfall from time to time. So we're going to move down a little bit south, stay within that same map area, but we'll be close to Inuvik. And we're on the edge of the Mackenzie River, and there's an escarpment of the Mackenzie River, which is known to people as the Caribou Hills. On the earliest maps, they're called the Reindeer Hills, but now everybody calls them the Caribou Hills. And on the Caribou Hills, there are a series of well-identified gullies. The first diagram of this was drawn by Sir John Richardson when he came down the Mackenzie in 1848 looking for Sir John Franklin. You know about Franklin, John? He carries your name. No?
Not familiar.
Not familiar? Jackie?
A ship or something?
Do you remember those couple of ships? Rachel? Can you remember? Katie, do you remember? Those guys, they found those ships in the Arctic a couple of years, 3 or 4 years ago.
Oh, I read
It's
it.
the harbor flag.
Yeah. Angie?
I would say right that National Geographic.
That's right. That's right. The Canadian Geographical Society, the Royal Canadian Geographical Society, they actually sponsored part of the expedition that actually found those 2 ships. Those were the 2 ships that got lost in the 1840s when they were trying to find a way through the Northwest Passage. And they lost the ships, and anyway, they found the ships again. But when the ships got lost, they needed to find, back then, 170 years ago, they tried to find the ships. So they sent people looking for them. And they didn't know where the ships were. They had no idea. They had no maps of where the ships were. They hadn't got a clue. So they sent some people from the east, and then they thought, well, maybe they made it all the way through and got stuck. So we'll send some people from the west to see if we can find them. And this is John Richardson, who came down, and he has a sketch of these hills in his book. So you can see these gullies that are on the hillside, and in his book, there's hardly any trees on the hills. And some people think that's also a sign of climate change, that it was colder back then. Anyway, Dr. Mackay, who I told you about before, in 1954, he was on the river, and his assistant, John Stager, took the picture that is on the left-hand side. That's in 1954. And you can see there's hardly there. You can see the gullies, you can see the vegetation. And on the right-hand side, there's a picture that Dr. Mackay took in 1963. You can see there's one landslide that comes down those hillsides. And if we look at the photos that have been taken since 1954, there's that landslide and there's one other. And then in 2009, they had a bunch of landslides. But in 2017, there was a big landslide in the end of the winter. And I took this picture a couple of years later in the summer of 2019. And you can see the nature of what happened there. And essentially, on the 25th of September, 2017, there was a big rainstorm in Inuvik. We know it was in Inuvik because they have a record there. There's nowhere on these mountains that they had records. But over an 11-kilometer stretch of that edge of that river, there were 87 landslides that came down that night. There were people camped at a small place along the river, and they said that they thought the world was coming to an end because they heard all these big noises all over the place. But fortunately, they weren't ever, taken out. So this is an example of something that was totally unpredictable. Nobody knew there was going to be a huge rainstorm. Nobody thought that there would be 87 landslides in a small area. The people who had cabins along here were really frightened. In fact, nobody lost a cabin, very fortunately. But it was as a result of what is a relatively very, very rapid event. And so if there's sudden changes that take place, then it's really difficult for us to manage them. And we can't adapt to a sudden change because look, otherwise they would have adapted in BC in the last week, but they can't adapt to it. And we see the results of what happens. Unexpected, not very well understood, and really difficult to predict. So that's where we have to think about resiliency. Because these sorts of things, if we're going to manage them, we have to manage them in advance without knowing that they're going to happen. We have to believe that what we're doing is the right thing because these things might happen. We can only imagine what would happen. I'm not using scientific language here. We can imagine that there might be an event. And so we have to protect ourselves against what is a potential rather than what has happened in the past and what is a practice. And that's a really difficult thing to get people who have to commit resources to do. Because if you say, well, actually, in order to deal with this, I need to build a $400,000 bridge, then they're going to say, $400,000? Forget it. and then we lose the road. Oh, well, that's a big inconvenience for people for 6 weeks. We should have built the bridge. Right? So it's a difficult thing to deal with resiliency. It's a huge investment, and it's not an investment that is necessarily based upon past practice, because our world is changing with climate change. Now, the other thing that is important, and what I've been talking to you about here, is actually ground conditions, things happening at the surface. But in permafrost, we also have lots of ice in the ground. And the big problem with permafrost and climate change is what happens when the ice melts, because then we lose the landscape. And there's an area of the Western Arctic where there's actually about 30 meters of ice under the ground over vast areas. And here you can see an example of an ice exposure that I had to take from the road with a telephoto lens, but it's on the far side of a little creek, and that is about 500 meters across on that exposure. It's bigger today, but that's what it was in 2012. If we go right up close to those exposures, you see that there's a steep wall where the exposure is, and that's sort of glistening, and that's ice. So it's ground, which literally on the top, you've got vegetation growing in a little area that thaws every summer, and that ground might be 60 centimeters, 2 feet, 3 feet deep, and then underneath it's just frozen, but underneath may also be almost entirely ice. That's one of the reasons why the permafrost environment is kind of sensitive, because if that ice starts to melt, then the water runs away. As it's ice, it's solid and fixed. But as it melts, then the water runs away, and then we're left with something like this, with all this mud flowing down, and that steep face, which is just entirely frozen material. So I'm going to talk to you now a little bit about some examples of what happens when that ice melts. And this is a little map of the Alaska Highway in southwest Yukon. So it's a bit near where Zach was going, although he didn't come in this direction, he doesn't think. So this is the Alaska Highway, right close to the Alaska border. So Alaska's on the left-hand side. And from kilometer 1679, which is at Destruction Bay, through to the border, it's about 220 kilometers. And it's the part of the highway which has had the most problem with permafrost thawing. And if you travel along the road, it looks a bit like this. And the road is meant to have a speed of 90 kilometers an hour. And if you take the front end off your vehicle if you go at that speed along this place. So what it means is that everybody has to go very slowly, and then after a while they get talking to the highways department and say, fix the road, it's terrible, fix it. Anyway, this road, this picture was taken in about 2008, but this road was rebuilt from 1999 onwards. So it's been rebuilt in the last 20 years, completely rebuilt. And when they rebuilt it, they spent, for the sections with permafrost, they spent building it about $1 million a kilometer. For the sections without permafrost, they spent a little bit less than that. And then they had to come and fix it up, because the sections with permafrost had thawing underneath them. So it was paved and it got busted, so they had to come and fix it up. So what they then did was spend another $300,000 per kilometer on the sections with permafrost, since they had built it new in the first place. So after about 6 years, they have to come back and rehabilitate the road. And it costs about $20,000 per year per kilometer to run this road when it's over permafrost. I don't think that's what they spend around here, right? They probably spend less than $4,000, which is what is the non-permafrost section. So per kilometer, it's incredibly expensive because of the degradation of permafrost. But those are gradual phenomena, right? That they can plan that, they can manage that, because it's a gradual phenomenon. But then there are some sudden phenomena like this. And this is a place where there's a sinkhole next to the Dempster Highway. And this is an enjoyable sinkhole for me because I remember seeing it in 2012 and talking to the foreman about it. And then in 2017, when I was going up, I went to Zach's friends in Whitehorse, and I said to them, what's the trouble with the sinkhole at kilometre 82 on the Dempster Highway? They said, there's no sinkhole there, we filled it up, it's just fine. And 2 days later, I was at this place, so I very gleefully took a picture, put my field assistant next to it, and then sent it to them when I got to Inuvik. Oh, they said, oh dear, because they can't run a road with a big hole right next to it like that. And this again is associated with thawing of the ground underneath, but also water movement, carrying sediment that is flowing underneath. Angie?
Is there a clay up there? Because it just sounds like a lot of things like Quebec having clay in their landslides and the saturation of the clay. Would any of this soil have clay?
So this material has a little bit of clay in it, but it's a glacial deposit, so it's a mixture of everything. Okay. It's much more closer to what we have on the surface around here, whereas the sediments below here, the landslides that you talk about in Quebec, there are some, the South Nation River, which is not very far, has a very famous one of those landslides, and they're to do with being a marine clay, being deposited when they were in a salty environment, and then having the salt taken away over 10,000 years of rainfall, and so the clay becomes unstable when it's had that fresh water replace the. So it's not quite the same, but they are both associated with the end of glaciation. Yeah, but as I say, this is a sudden one, and this is a difficult thing to deal with. You have to close the road to fix it up. So this is the sort of thing where you have to think about how do we manage the resilience to it. So that's infrastructure. But I'd like to finish by talking to you a little bit about what is the real issue with climate change and permafrost. Infrastructure is like easy, they're going to have to manage it, it's going to be dealt with. But there is this big problem that's looming, and it's to do with the fact that at the top of permafrost, there's often a lot of organic material, buried organic material. So it's material that used to be peat that is now in the ground at the top of permafrost. And in the next picture that I'll show you is one close to the coast. It was a picture I took actually at the ocean. And you'll see the line that says top of permafrost, and underneath you'll see it says organic material. And that black stuff, which is there, is buried organic material. Essentially, as the soil has moved downslope, the soil that is thawed every year has moved downslope, it's kind of folded over on top of itself and buried that material at depth. Now that burial process takes quite a long time. So some of this organic material has been degraded because it's been exposed to the atmosphere for a long time, but some of it hasn't. There are also places where the ground has had sediments placed on top of it and the ground surface has risen up. And that has buried other organic material. You can see in this picture, there are little rootlets that have been buried in the ground. They're now buried in the permafrost. And when they're in the permafrost, they're inert. Nothing can happen to them. But if we look overall, we see that in the permafrost regions, there's actually quite a lot of buried carbon. So this is the top 3 meters of the ground in the permafrost regions. And the very brown stuff, or the very red stuff that you can see on the slide, is where there's lots of buried organic material. So the Hudson Bay lowlands, which is a big peatland, has a lot of carbon in the top of permafrost. The Mackenzie Valley, which is also peatlands, has a lot of carbon in the top of permafrost. Russia also has quite a lot of carbon in the top of permafrost. Worldwide, there's a significant amount of carbon. The amount in all of permafrost worldwide, we think is about 1,500 billion tons, which sounds like an awful lot. It's actually a huge amount. In the top 3 meters, it's about 1,000 billion tons. And in the atmosphere, there's about 800, 900 billion tons. So it's sort of about the same amount of carbon as we have in the atmosphere. The problem is that our industrial emissions are about 10 billion tons a year from all of society. 10 billion tons from industrial emissions and 1,000 billion tons in the permafrost. So if we lose 1% of what's in the permafrost, that's the same as all of our industrial emissions. So it's now a big problem, because if that carbon starts to get released into the atmosphere, we have a big problem. And it's worse because things like the COP26 climate conference, they don't think about natural sources of carbon. They only think about anthropogenic sources of carbon. So we have a problem if this stuff starts to get released. And at the moment, we think that things are pretty close to being in balance. That is, that the amount of carbon that gets stored in permafrost is about the same as the amount of carbon that gets released. So the vegetation grows, and the plants store it in their roots, in their leaves, and in their woody pieces. And then in the ground, the bugs work away at the roots and the dead stuff, and they send it up again. And characteristically, we thought that there's a bit of a balance. We thought actually to start with that there would be more carbon stored because the climate's warmer, there should be more vegetation. But we think now that we're getting close to having net emission of carbon from permafrost. The suggestions are that it's still not a great deal, about 300,000 tons a year, not yet up to 1 billion tons a year. But it's one of these dangerous things where if we've only got a few places where we're studying it, so we don't really know, but we expect that it's going to happen, but we don't know that it's happening yet. But the problem is, once it really gets going, it's a big problem for all of our other commitments, because it might wipe out some of the gains that we've made in other ways. So one of the ways to look at the tundra of Canada, this is the Old Crow Flats, which is in northern Yukon, is to sort of imagine each of those polygons as being a little factory. Each polygon is a little factory that's emitting a little bit of carbon gas. At the moment, it isn't emitting very much because the permafrost is still frozen up. But its potential, a serious potential, it doesn't take much imagination to think that actually we're going to have a really serious problem if the Canadian permafrost carbon starts to make its way into the atmosphere. And it's not something that we hear a lot about. The politicians do not want to talk about it because it's not part of the protocols, because it's a natural source. And it's also a big problem for us because we got lots of it. The Russians have lots of it, and we have lots. Americans have a bit, but not many other countries in the world have it. But it's the reason the Portuguese are really interested in permafrost. You'd think the Portuguese are interested in permafrost? Doesn't make any sense. But they're interested because they know the consequences of permafrost for climate change are substantial. So, should we be concerned about permafrost and climate change? Well, we can learn some stuff. That's the academics think that's great. The researchers are happy about learning more. It's going to be expensive and it's going to be inconvenient. That's the infrastructure side of it. But it's not insurmountable. We don't have lots of infrastructure in the north, so we'd have to put another $1 billion there. But at the moment, the federal government is willing to spend $1 billion on fixing up roads so there's more mines in the north. Right? So it's a question of priority, but the money is available. But the problem is the amplification of the carbon effects. That's the really serious problem. And that's the reason why I think it's actually important. And I'd just like to finish with a quotation that you've probably heard before from John Donne. And it's for whom does the bell toll? Is the bell tolling because that guy died and is his family bothered about that? Or when somebody dies, does it affect you, whoever you are? And it's this phrase, no man is an island, entire of itself. that we're all part of the main, we're all part of this issue. And it's not something that we can say, well, that's the people in Inuvik, they should worry about that. Because what actually happens in Inuvik actually affects us here. What happens in Inuvik doesn't stay in Inuvik, right? It comes down. Because when the carbon as CO2 or as methane is released into the atmosphere, it's got no more boundaries. It's ready to go. And it'll be everybody's problem. So that is really the fundamental reason for why permafrost and climate change is of interest to the River Institute, even though the River Institute is a long way from the permafrost. So I'd just like to thank you so much for listening to me today.
Thank you. Okay, this is fantastic. So first things folks, any questions from the audience here that's present? No,
Maybe.
that's not a problem.
John had a question.
Maybe in a moment.
Oh, yeah, maybe in a moment, okay.
Okay, I'm going to put my ECCC hat on, Angie, and I'm going to ask you what the difference between climate adaptation, climate mitigation, and climate resiliency is.
Okay, so climate mitigation is reducing greenhouse gases. And the greenhouse gases are, at the moment, carbon dioxide is the largest industrially emitted greenhouse gas. The most important greenhouse gas in terms of total effect is water vapor, but that's in the clouds. And so we don't think we can control that. So that's sort of like part of the hydrologic cycle. It's a natural thing. Methane is the second most important greenhouse gas. So CO2 and methane. Then there are the nitrous oxides, and many of them come out of our tailpipes. But then there are also some gases which are very small in number at the moment. They're known as the fluorinated carbons. They're industrial gases, so they only appear since 1950. There's no record of them before 1950. They're the sorts of things that keeps our refrigerators cool, that circulate in the refrigerator. There's not very, very much of them in the atmosphere, but they're making an impact because they're dealing with some radiation wavelengths that the other gases don't deal with. So they're actually sticking there. So part of climate mitigation is reducing the emissions of those gases. And that's not a difficult thing to do if you can get people to agree, but that's the difficult thing to do, is to get them to agree. Because emissions at the moment are very highly correlated with our standard of living. So Canada emits per capita about 19 tons of carbon per year, of CO2 per year, per person. It used to be, 20 years ago, it used to be 20.5. So actually per capita we've gone down, but our total country emission is the same. And that's because our population has gone up. So our population rises, so even though we're emitting less per head, we're actually emitting the same amount. In terms of what it does to the climate, it means we haven't changed. We're doing the same thing. But China is now the world's greatest emitter of greenhouse gases. 24% of the CO2 is now emitted by China. That wasn't the case 25 years ago. Also Russia, the United States, and India. And China and India, it's because of the number of people. There are lots of people there. So even though per head, they might not be emitting very much, because there's over 1 billion people, then you get a lot of emission. So climate mitigation is reducing those emissions. That's the first thing. Climate adaptation is managing the effects that we think will happen. So climate adaptation is we anticipate that the snow will only come in January, let's say, and so we will have less water in the spring, in the snowpack. So what does a farmer do if the ground doesn't get wet enough? Right? That's adaptation, thinking about managing water. Adaptation is also about if we think that a culvert under a road is going to need a bigger diameter, we will put that culvert in there so that the road won't be washed out. when the big flood happens. But those would be things that we can think about, that we can anticipate, and that we're pretty sure is actually going to happen. Climate resilience is having a system, having a society that can handle what's thrown at us, which we didn't expect. I think it's going to be very interesting. Like, as an academic, this is a very dispassionate thing to say, and it's not a very pleasant thing to say. I think it's going to be academically very interesting to see what happens in British Columbia in the next 6 months to 6 years. They had this incredible disaster, but if we call it a disaster, it means we're not resilient. And so how do they change their systems of operating in BC? How do they change their infrastructure so that the next time this happens, it's not going to have the same impacts? And that would then be resilience. But that's you have to put a lot of money up front into resilience, and maybe the event only happens once in 20 years. Maybe it happens once in 30 years. Maybe it happens once in 15 years. Maybe in the future it happens every 5 years. One of the questions we'll have to address is, how often does something need to happen for us to make ourselves resilient? It's a difficult question. And it's associated with belief. Like, what do we believe is going to be the case? If we have really good every good understanding, and if we have good motivation for believing something, we'll turn it from resilience into adaptation. We'll say, no, that's absolutely going to happen. We're going to manage it. The big problem, I think, with resilience is that first of all, it's rainfall usually that we have to be resilient to. I mean, you could argue the forest fires in the West were also things we needed to be resilient to. Those things we can deal with by zoning. So then zoning would sort of be adaptation. We'll say the houses have to be so far apart. We can't have trees within a certain distance of the city, or we can only have a certain number of trees, or something like this, so that you actually reduce the chance of having a wildfire and knocking out your village. And it's not like that hasn't happened. So it's something we really have to think about. But resilience is, I like to think of resilience as as how do we prepare for the unknown, and I like to think of adaptation about preparing for the known.
Thank you very much. I've got 2 questions from the audience. Melanie, if the permafrost continues to thaw, we'll become vulnerable to peat mining.
That's a good question, I haven't yet heard of anybody who's proposing peat mining in permafrost. But in Whitehorse, near to Whitehorse, there is actually a peat farm where people, where they excavate peat. There is a strange, there's a strange implication of Melanie's question. Peat is a very, very good insulator. And if you want to preserve ice, one of the ways of preserving it is by covering it in peat. I don't know if that's ever been observed. I wouldn't be surprised if people around here have observed that. You know how when they used to have cellars where they kept blocks of ice, they would cover them with sawdust, and that would keep the ice there for long. Well, cover it with peat, you get the same effect. So one of the ways that it's actually possible to try and stop thawing is by covering things with peat. So it's one of the techniques that can be used for management of permafrost thaw. But if the thawing actually takes place, then yes, the peat could be mined. One of the difficulties is, and Melanie will understand this, is that peat has a very high porosity. That is, if you have saturated peat, about 80 to 90% or 70 to 90% of that is water, the volume is water. So when you have frozen peat, you've got lots and lots and lots of ice in the peat. And that makes it really difficult to thaw. So the peatlands will actually be areas that will thaw very slowly, even though they might be quite far south. And they thaw slowly because they've got lots of ice in them, and the surface of the peatland dries out, and then becomes a really good insulator. So peatlands are actually places which we wouldn't expect to see thawing happen quickly. So if Melanie's thinking of starting up a business, mining peat in the north, I think she's looking for some long-term investors.
Well, for Pete's sake, I've got a second. So this comes to us from Senator Bernadette Clement. She says, "Thank you, Dr. Chris, you're a terrific and clear speaker. Can you speak just a bit more about that lovely island with no emails? Does the study there continue? Who funds that? And what words do we need to use to catch the attention of politicians and community members to have them understand that this will and must cost really big dollars?"
So Ilsavik is the work that we do at Ilsavik is supported by 3 principal agencies. One is the Polar Continental Shelf Project, which is Canada's national logistics project for Arctic science, and some other activities, but primarily for Arctic science. And they've funded my work continuously since about 1991 or 1990, something like that. And we apply every year, and we ask, can we have some helicopter time to get us to the site, and then to bring us, hopefully also to bring us back. So that's one agency. The second agency is the Natural Sciences and Engineering Research Council of Canada, NSERC. They support the River Institute here. And NSERC is, you as a university scientist, I apply every 5 years to NSERC, and I give a proposal for what I'm meant to do. I tell them what I've done in the last 6 years, and they have a committee that evaluates it, and then they say, yes, we should keep this person funded. Or they say, well, I think it's time for them to retire. One or the other. But usually they've been very good to me, and they've said, something like that. So NSERC is the second one. The third is that in Inuvik, there is a branch of Aurora College called the Aurora Research Institute. And the Aurora Research Institute has a big area where I can store stuff. They've got a warehouse where I can put outside stuff, and then which can freeze nicely in the winter, and then they have a place indoors where instruments that are very sensitive or something, they can stay in there. And if I didn't have the logistics support from them, we'd be really sunk. And they also have people who can go and make measurements for you, and people who can come with you in the field. But I would also say is that in the Western Arctic, I have been tremendously fortunate that there's a young man, well, he's not so young anymore, but because he started working with me in 1997, called Douglas Esagok. And he's one of the best shots in the Western Arctic. So we've never been hungry. And he's traveled with me from Herschel Island through to large portions of the Mackenzie Delta. And he's been a wonderful traveling companion and worked in different places, very, very good. And I'm also very lucky in the central Yukon to work closely with the First Nation of Nachoniakdun. So that connection is actually a very important connection, and becoming more important in terms of getting the ideas that the scientists have communicated to the communities where they're actually living. So those would be the most important connections. Was there something I missed in the question?
Yes, that's okay. You answered it very well. The last part is, and what words do we need to use to catch the attention of politicians and community members to have them understand that this will and must cost really big dollars?
Well, there's the question of adaptation becomes extremely costly when we start to talk about spending $1 million for a kilometer. If there's a section of the Alaska Highway where the road is sitting on top of about 12 meters of ice. And in the last couple of years, they've put into the ground little things that that enhance the cooling of the ground in the wintertime and chill the ground. These are called thermosiphons. And basically they take fluid which is up in the atmosphere or in the top of the chiller, and it cools off in the atmosphere in the winter, and it then drains down as it's heavy because it's cold under the ground, it evaporates in the warm conditions under the ground, and then it comes back up as gas, and then it condenses and goes down that way. And in that way, that circulation enhances the cooling of the ground. Now, when they had to fix 500 meters of road, so half a kilometer, it cost them $4 million. So that means $8 million a kilometer. Now, if we're going to have to fix 223 kilometers of the North Alaska Highway, fix them with thermosiphons, that's 220 times 8. Right? It's a lot. $1.6 billion. Well, we better get the Americans on our side, because we're not going to spend that much money, given that Burwash Landing, which is one of the communities, has around a population of something like 400, and Beaver Creek, which is the other community in the area, has a similar population, maybe a little less. Beaver Creek, actually, all know about Beaver Creek. Can you remember why? Do you remember those 2 people a year ago when shots were coming out for COVID?
Yeah.
And those 2 people from Vancouver who flew up to the Yukon and then hired a plane, and do you remember that?
Yeah.
Katie, do you remember that story? No? Oh, well, anyway, it got all over the newspaper. It was in the Guardian. It was all a national newspaper. The guy was some kind of he worked in gambling. He ran casinos, I think. But anyway, he got to Beaver Creek and he got an extra shot. And then everybody got angry with him because he shouldn't have done that. Do you remember that?
Yeah.
Yes. Anyway, so that's Beaver Creek. And that's the small community with the White River First Nation and a few other people. And you can't spend $1.6 billion on 400 people, because otherwise you're going to have to spend $1,600 billion on Cornwall. Wouldn't you like that? Population 100 times greater.
Why do they even need that big highway? Why?
Well, it was built in the Second World War so that supplies could get to Alaska, and the Americans need a secure route overland from the 48th parallel, from the lower 48 to Alaska. So they need that road, and they needed it as a strategic highway so that in the event that there was some big problem, they could get military supplies to Alaska.
Yeah, so I think it's an American issue.
Well, the Americans have funded it in the past, and they probably will fund it again. But as with all of these things, it's political. And so depending on the flavor of the month, it's like, why are we giving this money to Canada? Or, oh yes, we should really be spending money on that. So it wobbles. There's an agreement that was signed in 1942 between Canada and the States about that highway. And the agreement, I think, says that the highway will be built with American money, but it will be in Canada, and in perpetuity, there will be no hindrance to travel along that highway.
By the Americans?
Yes, yeah. And so then, the Americans have an interest in having that highway in a condition which people can use it. I mean, and there's lots of trucks and stuff that go up and down the road.
Yeah, I mean, it's important, I would imagine, for the communities that are there. It's important to service those communities, but it just seems kind of ridiculous to continue with that highway.
Well, the question that people have to ask themselves is, do you want to have a highway above permafrost where you can travel at 90 kilometers an hour? Or do you say, we don't need a highway with pavement, we can deal with a gravel road, we're going to drive at 40 and we're going to get there sometime. We're going to have we're going to get better music to listen to, and it's going to take us twice as long, right? So that's one of the issues it's an adaptation question. The adaptation question is, you don't necessarily have to have the same service standard, but you may lower the service standard, but still make it possible to use the road for the purpose for which it was intended. And that is an adaptation response. the question is it a response that people are happy with? And the trouble with people is that once you've had the deluxe treatment, right, you feel you're entitled to it. So it's really difficult if you're accustomed to, like, I'll tell you what these guys did to me today, which is kind of like a tricky thing. I went to get I asked them, can I get a rental car to come here? And I was thinking I was going to get some little Chevy tiddly thing that is, just for one person, that's all I need. Well, I get into the rental agency in Ottawa, there's a Mercedes waiting for me. I'd never driven a Mercedes in my life. I've probably been in a Mercedes 3 or 4 times in my life. Very smooth drive to here. Well, I'm going to go home, I'm going to park it in the drive and take it back to the place tomorrow morning. But if any of my neighbors, they say, oh, Chris, you bought a Mercedes, then they're going to expect me to have a Mercedes in the drive for the rest of my time, right? Well, but it's a very pleasant car to drive. I'm not going to say nothing about that, but it's like, I'm not entitled to a Mercedes, right? But I could get used to a Mercedes very quickly. And in just the same way, we're used to driving along a road at a particular speed. And so then to be told you can't do that, you have to go now at a lower speed, then it's like, this is a problem for me. But that's the kind of question that gets used in adaptation. It's like, how do we adapt? Do we have to have the same service standard or not? And what's happening when we do that actually is interesting, because what we're saying is, if we have the road at 90 kilometers an hour, we're spending $20,000 to $25,000 per year per kilometer on maintaining that. If we degrade the service standard, the cost is transferred now to the driver, because the driver's driving along the road like this, and they're slowing down. And if they go at 90 kilometers an hour and have problems with their vehicle, the expense is theirs, it's not the government's. Right? So there's a little bit of shifting of responsibilities that happens in that particular context. But I think it's a question of what does adaptation mean? How do we manage changes? Do we just expect that life will go on exactly the same as before and somebody else is going to do all the management? Or is there some elements of this that, because it's the world that has created this problem, this climate change issue, it means that it's the individuals in the world who are going to have to handle the management of that problem? Or do we all say, it's not my problem, it's the government's problem, right? And so that's one of the questions that we have to face. And from my perspective, it's difficult to see how it can be all just delegated to some other agency. It's just difficult to see that. But that doesn't mean that's not how other people think about it. Did that answer the question?
I believe it did, my friend.
Okay, good. Phew.
I'm not going to ask you the same question in French. Are you ready? It's okay. It's good. We'll practice together. So, are there any other questions in the live audience here? Angie, ECCC hat. Any questions that you want to throw out there now? Perfect. All right. Well, then I'm happy to conclude this. Zach, I'll come to the front and say goodbye to everybody. You want to push that button for me?
I'll get out of the way.
A very special thank you to those that are at home that have taken the time to enjoy this conversation. Hopefully this has proven insightful to you. On behalf of future climate leaders, we invite you to the next town hall that should be coming up next Tuesday. Other than that, please pay attention, and if you have any questions, please reach out. On behalf of the River Institute, the community of Cornwall, and those present in this room, a very big thank you to Dr. Chris Burns. And while you folks are here, a round of applause. And we wish you all a happy good night. Thank you so much. Take care.